I've started the recording. Yes. I'll share my screen. Is my screen visible, sir?
Yes.
Okay. So present. I'm sorry if there will be any lag. Please let me.
Heavy graphics heavy.
Okay. Sir, is the PPT visible?
Yeah.
Okay. Good morning, everybody. So this is Group 5, Maritime Patrol Aircraft. So I'll briefly describe how we have done the takeoff weight estimation for Maritime Patrol Aircraft. So these are the design specifications which were given to us, and we were supposed to do two roles for this aircraft, that is military reconnaissance and rescue. And while doing military reconnaissance role, we were supposed to carry some payload like 2 missiles, machine guns for targeting ships and pirates, and anti-submarine capability, in which we will be carrying the torpedoes so that we can drop. And this is for military reconnaissance. And for rescue mode, we have to carry 3 stretchers, medical aid, and the aircraft should be able to support 10, should be able to take 10 passengers and who are in emergency, and we should give first aid to them and carry them back to the shore. So and start. So this is the reference aircraft, maritime patrol aircraft that we have used. I mean, the data we have taken from this aircraft as a reference to estimate the takeoff weight. So this is P3 Orion. Yes. So yeah, so the first role is the reconnaissance role, and this is the mission profile for this role. First, we're going to take off, that is 1, 2, and then we are going to climb and acceleration to cruise. And then this is 3 to 4 represents the cruise phase, cruise out, and we are going to accelerate it to maximum velocity. Since maximum speed was given to us as a design specification, we are going to accelerate it to a maximum speed, which is the intercept, and then followed by we are going to loiter. Since endurance is one of the main parameter for maritime patrol aircraft, this loiter time is what changes the weight of the aircraft significantly in this phase. So so this aircraft is going to loiter, and it is, as this is going to patrol the seas, so we need maximum loiter time as to find out where is the enemy ship or anti-submarine, so that we can do combat. So this loiter time we have chosen as 10 hours, and this is based.
Oh, reconnaissance. Okay, 10 hours time. Okay.
Our reference aircraft had an endurance of 20 hours. So yes, sir.
Yeah, sure. Okay, good.
Yes.
Good. Yeah.
And then we are going to climb down, descent at an altitude of 3 kilometers, and this combat takes place for around 10 minutes. So during this phase of combat, we are going to drop our missiles, 2 missiles, machine guns. We are going to fire the bullets from these machine guns. So, and we are going to drop torpedoes in case we find any submarine which is entering into our territory. And then we are going to climb up again.
So you're assuming you're offloading all of that?
Yes, sir. We are offloading all of them.
That
And
is, we call it
we are carrying initially, sir. We are going to drop only the bullets here, obviously.
Yeah, yeah. So only the what is it? The expendable payload and non-expendable.
Yes, yes. I have included that, sir, in the coming slides. Yes. Okay. And 6 to 7, we're going to climb again to the cruise altitude of, and the service ceiling given to us was 11 kilometers. So we have chosen our cruise altitude to be 10 kilometers. So we are going to climb again to 10 kilometers and loiter before landing and then land. And the second loiter time is around 1 hour. So
this military one, right?
This yes, it's a military one. Yes.
So even 30 minutes is okay. Anyway, then 1 hour it's okay. 30 minutes is fine. If you want to reduce fuel weight a little bit, you can take it 30 minutes.
Okay, all right. So this is the weight formulation, and the initial takeoff weight is assumed as 40,000 kg based on the data from reference aircraft. And the payload is, we have a non-expendable and expendable payload. Expendable is the one we are going to drop during the combat phase, that is 2 missiles, which is around 3000 kg, and torpedoes around 1200 kg. So 4200 kgs are expendable payload. And the given payload, the payload of 500 kg was given to us, which includes the crew and the cargo, and that was around 500 kg. And then we are going to carry some cameras, since it is going to do the surveillance job also, to find out the enemy aircraft. So we need cameras, although the weight of cameras are negligible, but like together, put machine guns and cameras put together, it is around 11 kg. And this is the non-expendable 511 kg, and total payload weight comes out to be 4711 kg. And now we are going to, so the approach we have followed is similar to the approach given in Cork book. We are going to, we are not finding the fractions. Yes, we are finding the fractions, but we are estimating the total weight of the aircraft after each phase. And then the difference of the initial assumed weight and the weight of the aircraft after the phase gives us the fuel consumed in each phase. And then we are going to add up the fuel consumed in every phase to get the final fuel weight. So for engine start and takeoff, we have chosen the ratio to be 0.975, which is within this range. And we have multiplied this with the initial weight. So the weight of the aircraft after this phase is 39,000 kg. And then for climb and acceleration to cruise, we have found out our Mach number at 10 kilometer altitude, which comes out to be 0.46. So based on this graph, and there's a formula which is like based on curve fitting, which is this formula is for this curve, that is WF by WI is equal to 1 minus 0.04 MF. This is also taken from the Cork book. We know our MF, so we found W3 by W2 during the climb and acceleration phase, that is 0.9816. So the weight of the aircraft after this phase would be 38,282 kgs.
You actually keep track of weight of fuel also after how much.
Okay, sir. Yes, sir. I forgot to mention here, but I'm adding all those to the end.
Okay, okay. That is most important.
Yes, sir. Yes. I have tabulated those things, sir. So
okay.
Yes. And cruise out to destination, we are going to, since we are flying at 10 kilometers altitude, we are using turbo fan engines, 2 turbo fan engines, which can provide a maximum thrust of 125 kilonewton each. And the TSFC was chosen based on the reference aircraft, which is 18 into 10 power minus 6 kg per Newton second. And the lift by drag ratio is 0.94 times maximum lift to drag ratio. And aspect ratio is 7.5, again taken from reference aircraft. We have calculated L by D, which is around 16.13. The total range it was given to us was 4,500 kilometers. So for the forward cruise, we have divided this by 2. So it is 2,250 kilometers for the forward range. And based on this gives us the weight fraction, fuel weight fraction for the range, which is 0.982. So the weight of the aircraft after this phase, cruise out, is 37,593.32 kg. And when we are accelerating to the maximum Mach number, that is 0.65 and 700 kilometers per hour, we are using this formula. We are multiplying W max by W.1, which is nothing but weight fraction for accelerated velocity. And this weight of the aircraft after this intercept phase is 37,367. And then loiter before combat is, as I mentioned, we have chosen the loiter of 10 hours, since endurance is one of the major parameter for the design of maritime patrol aircraft. So 10 hours endurance, and TSFC and lift by drag ratio as mentioned in the cruise phase. So the weight ratio comes around 0.96. So weight of the aircraft is dropped to 35,873 kg. So there's a significant difference of around 2,000 or 1,800 kgs compared to the previous phase because of a 10 hours loiter. And combat. So for the combat, we have used the same formula which is mentioned in the Cork book. Wi minus Wf is equal to C max into T max to time of combat. Time of combat is chosen as 10 minutes. And we are going to combat at an altitude of 3 kilometers. So this calculation gives us the difference in weight as 2,700 kg. Since we have to incorporate this difference in weight, we cannot work on ratios, and that is why we have chosen the absolute weight of the aircraft after each phase, so that we can subtract here. If we had chosen ratios, then the subtraction would have not been possible. And then here we are also dropping our expendable payload, which was 4,200 kg, comprising of missiles and machine gun bullets and torpedoes. So this subtraction gives us 28,973 kg. Then followed by climb back to cruise altitude and cruise back, loiter and landing using the same approach as we did for the first half. And the final weight after landing comes out to be 27,188 kg. So we got the final weight of aircraft after landing. We have assumed an initial weight of 40,000 kg. So the difference, and since I am also accounting for expendable payload weight, the total fuel weight consumed is given by this formula. And 1.06 is because of we are assuming 6% allowance for reserved and trapped fuel. And so the total weight of fuel consumed is 9,128.49 kg for this mission. Now we are going to calculate the empty weight. So the required empty weight is calculated based on the structure factor, which is given by this
Okay. Sanjay, we know this step. Only
Okay.
thing is, now what we want to know is what is your fuel weight fraction and empty weight fraction.
Yes, sir. So the required empty weight is given by this, and available empty weight as initial takeoff weight minus fuel weight minus complete payload weight. So
Okay,
this
finally, I'm telling. Finally, after
yes,
all the iterations, we know you did iterations. We are clear now.
yes,
But
sir. Iterations.
tell me a last one.
Yes. So there are like 12 iterations we have performed, and it converges at the end of 12 iterations where the total takeoff weight is 19,449 kg, and the available empty weight and required empty weight is same, that is 9,060 kg.
But then what is the fraction now?
Uh,
90,000 by 19,000. How much?
yes, sir. So that fraction I have not computed. I think.
You can compute now, no?
Oh, yes,
Yeah.
sir. So I'll just 9,060. Sir, it comes out to be 0.465.
Okay, great. Okay,
Yes.
thanks.
So
So
this
now,
is the total. Yes, sir.
okay. After others ask questions, I'll make 1 or 2 comments.
Okay, sure.
Okay.
So the final takeoff weight of the aircraft, the end of these iterations is 19,449, and this satisfies the convergence criteria which we saw during the lecture. That is, the difference of assumed and total takeoff weight should be less than or equal to 0.01 of assumed takeoff weight. So that well satisfies the convergence criteria also. Yes, so this here ends the combat mission, and now we are going to do the same procedure for the rescue mission, and then finally I'll explain why we have chosen combat mission as the primary mission for the design. So for rescue mission, it's the same mission profile up to this loiter, and then it has to land somewhere. So what we have planned is, like what we have designed is, it's going to land on an island which will be, I mean, in the ocean, and the people who are in emergency will be carried over to the island by some ship which will be loitering in the seas, and we are going to take those passengers who are in state of emergency. We are going to rescue them.
No. You can't build an island. You assume it lands in water, and you can take those people right from the water.
Okay, okay, sir. So in that case, it has to be an amphibian.
Yeah. Landing only. Yeah.
Okay, sir. Okay. So we are going to include some 10 passengers. That was what was specified in design. So 10 passengers, weight is around 1000 kg. And then we are going to take off with them and climb, cruise, loiter, and land.
When we used to design, we took the passenger weight as 80 kg. Nowadays, I think people have,
Yes.
are more well fed. Yeah. Okay.
There are fat.
To put it politely, no. Okay.
Okay.
No, the lifestyle has become more sedentary now. Don't run around.
Yes.
Everything you can do from a computer. What
Yes.
pastime do you have? Eating.
Yes, sir.
Okay. They don't get into that rut, because
Okay.
I myself was obese once upon a time. Then
Okay.
to get down is a little bit difficult. Okay. Yeah. Okay. Fine.
The initial takeoff weight assumed for this is 20,000 kg, and since the same aircraft which was doing the combat mission has to do this job also, we have taken the empty weight, required empty weight for this phase as the same empty weight that we got from the combat mission. Since all other parameters remaining the same, we are only going to change the payload and the fuel according to the payload. So the required empty weight is taken from the combat mission, which is 9,060, and we are fixing this. And as we are fixing this, and we are going to see how the takeoff weight and fuel weight consumed in this phase is going to change. So the payload is like non-expendable payload. We're going to have crew, and since we are going to take passengers who are in like urgent medical emergency, we should have two medical attendants at least who can give them first aid. So we have to include the weight of two medical attendants and medical equipments, which will include first aid and three stretchers. So all this put together comes out to be 825 kg, and weight of passengers is 1000 kg. So expendable payload is 0 kg. We are not going to drop anything during our journey. So the total payload weight is 1825 kg. And then these are the same some specifications for this mission.
Yeah.
And again, we are going to find out the weight of the aircraft after each phase, as we have done for the combat mission. So I'm just skipping this are the same procedure. And here I have included for the addition in weight of the passengers. So the
Here
final.
also you are subtracting the weight, no, not multiplying the fuel weight fraction.
No, sir. I'm adding here actually. There I was
Adding
subtracting.
weight and yeah.
Yes. Sir. So the total takeoff weight at the end of first iteration is 15,299 kg. And then as the empty weight was already fixed, I have to just adjust my available empty weight. So
Why same weight fix it?
sir, because the same aircraft has to do this mission also. So the empty weight that we got from the combat mission, we took it as a required empty weight for rescue mission.
This is a secondary objective you are taking. That is the primary objective, secondary one.
Yes, sir. This is a secondary objective.
Okay.
So yes, sir. So the
empty weight you are taking it to be the same.
Same, yes, sir. Required empty weight, which means the avionics and all the structure weight is going to remain the same.
Yeah, okay.
We're not changing the engines and all that. So it's the same aircraft which will do this job. Only thing is we are going to vary the payload and the fuel according to the payload. So
yes. Fuel you cannot increase more than what's available.
Yes,
you have to live with what fuel is available.
So here the fuel weight is pretty less than what we had for the combat, because during the combat phase 2700 kg is consumed. So this here, I mean, for that, no sir, during the combat mission, in only that 10 minutes combat phase, like huge fuel is consumed.
No. Yeah. So what is the total fuel weight for the earlier?
So total fuel weight for this phase is 3118 kg we got, and total takeoff weight is 14,000 kgs. So here
the other one, where the fuel weight for the other one.
Yes, sir.
Okay. So you are safe. No problem. Yeah.
Yes, sir.
Good work. I really appreciate this work.
So this is the comparison for combat and rescue mission, and you can see the total takeoff weight for rescue mission is almost 5,000 less than the combat mission. That is because we are not carrying any.
So concentrate only on fuel because empty weight is same.
Okay.
So that is you are safe. That in a sense, you can take the primary. You can just design for the first one now.
Yes.
Combat mission. It will automatically rescue mission will be satisfied. Okay.
Yes. And as it was specified during the rescue mission, we are supposed to offload this armaments. So we are not carrying missiles and all, and that is why the payload is less for the rescue mission, and hence the fuel weight is less.
Okay.
So this is. Thank you.
Yes, questions? Yes, someone has raised the hand. I don't know who. NS. Who's NS?
Sir, this is Niveta.
Yes.
Niveta,
I just wanted to clarify one thing. So when you take the assumed takeoff weight initially, you are computing it. You're computing the fuel weight. You're computing the weight after each segment, right?
Yes.
So when you do the iterations, you've all these steps are followed. As in, you'll find the weight for each step again.
Yes.
Okay.
Yeah, I'm finding this. No. So since this fuel weight fraction ratios remain the same for all this phase, I don't have to do the same job again. So I'm just multiplying that ratio, and I'm like multiplying with the preceding weight. Like for example, I've done this as a spreadsheet. I've not put it here. So I've just changed.
That's okay.
Yeah. So I've just changed the assumed takeoff weight for each iteration, and the total fuel weight was computed. All the steps remain the same. You're not changing anything in between.
Okay, so you'll be finding the fuel weight fraction as well for each segment.
Yes.
Okay.
So So thank you, Niveta. What's your roll number, Niveta? Can you put down your hand?
27, sir.
Yeah, okay. Then Adarsh, what's your roll number?
1, sir.
Okay, okay. You can ask
I
the
ask
question.
one question?
Yeah, please.
So,
Yes,
can you just go to that mission profile for your rescue mission?
rescue. Okay. Yes. Yes.
So, what actually happens is in that 8 and 9, it's actually that cruise back, right? So, you're just
Yes.
going to the
Yes.
destination.
Exactly.
So,
Yes.
what I feel is like, as Sir just mentioned a few minutes ago, he just said that you will be landing in the water, right? So, it's an amphibian aircraft.
Yes.
So you don't have any chance of refueling. So there will
No.
be a considerable amount of fuel already being consumed. So
Yes.
what I'm just asking is, so will the L by D ratio and whatever velocity you are like, if you are assuming the 8 to 9, the cruise velocity, will it be the
Yes.
same as 3 to 4, or have you changed it, or like what you
Uh,
have done it? So the L by D and
yes.
the velocity,
So yes.
cruise velocity.
Okay. So you're asking if we have taken the same L by D and V for 8 to 9 as we have done for 3 to 3A.
Yeah, you have taken the same LBD, or you have changed
Yeah,
it
we've taken
and
the same L by D and V. I agree that since the weight is lost here, so L by D and V should change ideally, but then that change is negligible, and like at this stage of design, we can assume the same L by D and V. That's what a point was mentioned in the Cork book. And also what I've thought is like we know the formula for V, that is square root of 2 times W by S by rho CL. So since weight is being reduced, we are going to climb the altitude. So when we climb, your density is also going to reduce. So W by rho, the ratio almost like remains not exactly is equal to 1, but it remains constant such that your velocity, the change in velocity is not appreciable during 8 to 9. So using the same V, and for L by D, again we have assumed the same L by D. Again, the difference won't be. I mean, even if we incorporate the difference, the fuel weight fraction is not going to change appreciably. Sorry.
Yeah, so you make that approximation during weight estimation.
Yes.
Is it for which phase of flight is it?
For rescue, sir, and as well as for
No,
combat.
no. Yeah, okay, 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 yeah, okay, no problem. No.
Yes.
Only if you are to find the, what is it? Yeah, I agree.
Yes, sir.
So
Because
the percentage change in fuel,
yes,
will be only 1 or 2% difference.
exactly.
Less than
And
so
like they mentioned, at this stage of design, we can assume the
fuel.
same use of L by D.
Correct. Sugandhan, your question?
Yes, sir. Am I audible?
Yes.
Yeah, please.
Sanjay, can you go back to the loiter weight estimation of the combat phase?
Okay. Just a second. Yes.
Share your screen.
Yes,
Sanjay.
I can see this. Can you say what L by D you used here?
L by D is what I have estimated initially. That is 16.1322.
But for the cruise and this, you have used different L by D.
No, I'm using the same L by D.
Yeah, that's what my question arises. Because for during loiter, we usually take the maximum L by D, or the L by D ratio will be higher than that of the cruise. You told you have used the same L by D. That's why I asked this.
So correct. Because for
Yes.
cruise, you use 0.94 of the LVD max.
Yes, sir.
Yes.
0.94 of the L by D max.
Did you use that 0.94? That's his question.
And is that a constant altitude cruise, or you are climbing some altitude while cruising?
No, that's a constant altitude cruise.
And I guess that's 0.86 of L by D max, if I'm not mistaken, according to Nikolai. And Cork
Okay, you
also
can.
states, yeah, from Nikolai.
No.
Cork takes 0.94. Yeah, you can
0.94.
use.
Okay.
If you take 0.86, you have to give the references Nikolai properly.
No, sir, in Cork it says he has taken from Nikolai. In Nikolai it says 0.94 is for altitude in which it climbs, and 0.86 of L by D for a constant altitude.
Good. No, what I'm telling is, it's good you have read. So when suppose he is using 0.86, okay, because it's not given in Cork, he should refer it properly to Nikolai. If he's taking
Yes.
0.94, he can just put Cork. We all know Cork's book. He doesn't have to
Yes.
refer it.
Yes, sir.
At this stage, I don't insist. whether it should be 0.94 or 0.86, it is entirely his discretion.
Yes, sir. That's my question.
Good.
Okay, yes, Sugandhan, so for and this L by D here, I've used L by D max, and in the cruise phase, I've used 0.94 times L by D.
Yeah, Sanjay, then no issues.
Okay, good, good.
Thank you.
Then, Sanjay,
Yes, sir.
when you convert your PSFC to the units per hour, how much is it coming?
Per hour, just
Hmm.
it's 18 into 10.
Convert kg to Newton,
Yes, sir.
then
So
you
it
get
is
it per.
0.65 around it's coming.
Is it so less?
So you mean
18, 10 power 6, 10 power minus 6, okay.
yes.
Multiply by 9.81, what are you getting?
Okay, 1 second. Multiply by 9.81 is 1.7 into 10 power minus 4.
Okay, now multiply by 3600.
Yes, sir. 0.635.
0.635. Yours is what type of engine? Turbo?
Turbo fans. Turbo fan.
Okay, good. No problem. Okay, great. Okay.
Any other?
Ashwin Sridhar, we are running out of time.
Yes,
Yes.
sir. Just a
Quickly,
quick
last
question.
question.
Since Sir changed your mission to where you have to land on water, so since
Yes.
it's a semi-amphibious aircraft, don't you think engines will be affected by water landings, and that turboprop would be a better choice for this?
Yeah, you're right. But in our case, like since I have mentioned, I chose the primary mission as combat mission. So the same aircraft should be able to do this job also. So that case, I'm using turbofan engine, and I'm not changing any other structural or engine specifications for the my rescue mission. I'm changing only the that is non-expendable payload and the fuel. So that's why I've chosen the same engines. Otherwise, this is going to like cruise at some 3 kilometers altitude. Like we're not going to cruise at 10 kilometers as like for combat mission for rescue. So yeah, I agree that turboprop would be more efficient. But then since we are using the same aircraft to do this job also, we have chosen the same engines.
Okay. Thank you, sir.
Thank you. Your teammates work well with you?
Yes, sir, definitely. All of them contributed.
Okay, good. So now, thanks for the excellent presentation, Sanjay. Although it took a bit long,
Yes.
I know this is a complicated one, so that's why allowing some more time for something. Nitin's case, probably, it was too simple for this weight estimation.
Yes.
So I didn't give, but as long as I feel that the class can learn, I will give more time.
Yes.
Only for the initial few phases.
Yes.
Each design will have its own complications. So just by reducing time, I don't want to, reduce the learning curve.
Yes.
So I just make some very probably not fair decisions, but I will try to be as fair as possible. As I always say, life is not fair, and aero design is also not fair. But I try to divide the unfairness as fairly as possible between you.
Okay, sir.
Okay, yeah.
Thank you, sir.
Welcome. Bye. So then, business jet.
Sir, can you hear me, sir?
Yes, just a minute. I can hear you. Are you sharing your screen?
No, sir, I will share it right now.
Yeah, okay.
So can you see my screen, sir?
Yeah.
So
Ashwin
good morning,
Kumar,
everyone.
I
Yes,
forgot
sir.
your face actually. I forgot your face.
7, just a moment.
Never mind. Later. Huh? Ashwin, don't worry. Just go ahead. Ashwin Kumar. He removed his headset. My mistake. Yeah.
Can you see me, sir?
Yeah. Now I know you very well. Yeah.
Yes.
Continue, please. Yeah.
Yes. I'll turn off the camera.
Yeah. Thank you.
So good morning, everyone. I'm here on behalf of Group 7 to explain the weight estimation we did on the business jet, which we are given to. Yes. First, the mission profile. So it's basically a simple mission profile consists of
Right.
takeoff,
Now
climb.
go quickly. Yours is a
Yes, sir.
simple
Yes.
one. Okay.
Yes, sir. I'll go it fast, sir. So the specifications which we are given for it is the route is between Mumbai to London, and it's a non-stop route. The distance is approximate of 7,215 kilometers, which we have rounded off to 7,300. And the number of passengers is 25 with 3 crew members. And the duration, which is 7 to 8 hours, which is given for us. So regarding this data, we have chosen L by D approximately 15.6 from this table. And the weight fraction we have chosen from the jet transport. Just a moment if you can't see it. Yeah. It's 1.02 for A and minus 0.06 for C. These data were taken from Cork book. And the equations which were used are the Breguet range equation to calculate the weight fraction during
Okay. Go to the next one. We all know. This.
So these are basic things we have taken, data we have taken. So we have assumed the M naught as 32,000 kilograms and the payload weight of 4,000 kilograms and L by D of 15.6. The range is 7,300 kilometers and the loiter endurance of 40 minutes. The velocity of 289 meter per second, which approximates to 0.85 Mach.
And how did you get that velocity?
Yes, sir. So what I basically did was we have both the range and the duration for travel, sir. So from that I calculated the velocity which is required.
Well. You are now giving away your teammates. They have not worked on this, correct? Only you have worked.
No, sir, they have, sir.
Then you say I have done. That means they have not done anything.
Sir, I have done these basic things, sir. Other iteration purposes they have done.
So you should put we have done. So you can talk to your team. Okay. I just a small thing I want to correct.
Yes,
yeah.
Normally the presentation
very careful because there are people who complained about this to me. Not you, but in earlier batches I'm telling.
Okay, sir.
This batch nothing. Sir, yes, he's telling I have done. So don't think, sir, we have done everything, but he's telling I have done, sir. So all these complications have come earlier. Okay, so because people hang on to every word you say. That is why. Okay. Sir. So some people I will just correct a little bit.
Okay.
It may land you in trouble. That's why I'm telling you. You just change that one word. We have done. Okay. So even if others haven't done anything, they may compensate for you later. Okay.
Okay, sir.
Okay. Yeah. Thanks. Tell we have done.
So we have chosen the SFC of the engine to be 0.25 per hour. So these are the basic values which we took for the calculation.
What type of engine? What type of engine is it?
It's a high bypass turbofan, sir.
Okay.
Yes. Yes, sir. So these are the weight fractions which we obtained during the calculation. So the takeoff, climb, and landing, these three values are given in the book Cork book, and it was also similar in the book Reimer. So those three values we took it directly. And for cruise and loiter, we used the Breguet range and endurance calculation. That formula we used and calculated it. So from that we calculated this is the total fraction, and this is the fuel fraction which we have got for this.
Okay. Probably the fuel fraction is a little bit high for you. It's okay, still acceptable limit. Okay. It is a bit high, probably because of long distance you have to report?
Yes, sir. Yes, sir. I too thought first it was kind of high. Then I understood that because we are trying a large distance, it will take a large amount of fuel for that.
Okay.
Yes.
Hopefully, you have done the conversions correctly. That's my main worry is people may
Yes.
make mistakes in taking the units. They may miss a
Yes, sir.
factor of 9 or 10 somewhere. Then it will make a lot of difference.
Yes,
You
sir.
should not have made any such difference. Told me the calculations clearly in the report.
Okay, sir.
Yeah.
I mean, this is just presentation, so I thought just like
Yeah. The units you take for velocity, range, and C, SFC should be consistent. They should be, or TSFC should be consistent.
Okay. I
If
mean,
you do it properly, they should be in the same units.
Okay, sir.
Okay, make sure of that. You'll be right.
Okay, sir.
Okay.
Yes, sir. Then these are the iterations which I have performed. So the empty fraction stops at 0.5529, and the calculated M naught, it converges at 27,040 kilograms.
Okay.
That's it,
Good.
sir.
Okay, good. Any questions? Yes, any questions to Ashwin? Okay, there are no questions. Thank you. Thank you, Ashwin.
Thank you, sir. Stop presenting.
Yeah. So this is do we have time for more presentation? Interceptor, Niveda?
Yes, sir. I can try to keep it short.
Okay, sure.
Is the presentation visible, sir?
Yeah.
Okay. Good morning, everyone.
Show me your mission profile. Then we will
Yes,
see
sir.
whether
It's the
simple one.
okay.
Okay, yeah. You are dropping weapons and all that. Then it may be a bit complicated.
Sir, I've taken that to be the worst case scenario. Only one mission profile, which includes combat. Sorry about the noise.
No, that's okay.
Okay,
That's
so,
okay.
okay.
What I thought was, whether the combat is necessary. Just okay, it's good. Yeah.
Okay, so these are the specifications which was given by Sir once we finished the initial design review, and these are the estimates which we have taken. The first payload is expendable. Sorry, I mean the pilot and radar should come in the non-expendable part. The expendable payload includes missiles and maybe bombs if we have accommodated for that as well. And the non-expendable payload has 2 crew members as well as 1 gun. This is the mission profile that we have designed for this interceptors. Initially, takeoff climb is all similar, and cruise and high-speed intercept we have in segment 3 to 4. After which we have a loiter before combat. Now, how this interception works is once the enemy aircraft has been detected, the ATC gives commands to the aircrafts to go airborne and tap into the frequency of the enemy aircraft so as to give verbal commands to chase them away. If those verbal commands are not given any heed, there will be the ATC can give instructions to the the pilots to initiate combat, which is why we've given a loiter as well as combat right after a loiter. The loiter is in case there is since before combat there should be some time to chase the aircraft. That's why there is some loiter, and after which there is combat. And then we have this similar cruise and then descent and landing. The first wait for takeoff and climb, since everyone, it's common as everyone, I haven't mentioned it in the report, I mean the presentation. We've taken it from the book Cork, so it's the same as what is there in the book and similar to everyone else's. The cruise, the range given to us was 1500 kilometers, and we followed this Beckett range equation. And since we have two different cruises in our mission, we've taken one half of the range for this first cruise. After this is loiter in segment 5 to 6. For the first loiter, which is before combat, we've given about 25 minutes for the loiter, and we found the weight fraction to be 0.964. The second loiter comes during descent when the this is some allowable time for before landing.
If
So
it's loiter before combat, you just really reword it.
Oh, sorry.
Not
Yeah.
loiter
Sorry.
before. Yeah.
So the first one is loiter before combat, which goes on for 25 minutes. One before landing is for 20 minutes. And these are the different weight fractions given for that. Now, during combat, in the formula given in the textbook, we don't have a formula for finding the weight fraction. Instead, we have a formula to find how much fuel is used during combat, which
So
is
it
what
is
is given
similar
here.
to what
Yes,
Sanjay
what
has said.
Sanjay did.
And
Yeah,
this
but
Ross,
instead of
you put a Jan Roscam book, no? It is
yes, sir.
JAN. Huh? I just wanted to tell the whole class that is kind of Bible for airplane design. Okay, so Jan Roscam, please note, it's a very good book. There is probably
Yes, sir.
from whom everyone has. So, did I give this reference to you? No.
No, sir. We searched for one paper
Good.
where this was done, so in which this was referenced.
Fantastic. It's a very good book. It has many parts. Okay. 5
Yes,
to
sir.
6
This
parts.
one was only for preliminary weight estimation.
Yeah. So it's. I just want to tell the whole class. You share the class the link from which they can get. Later, if someone wants, they can readily this thing. So much data is given. Anyway, it's a very old book, but still very relevant.
Okay, sir.
Okay. Thank you.
Yeah, I'll share it with the class. So in the book, they'd taken for combat, they'd taken the to find the fuel weight fraction for combat. We don't have a value of weight as such, which is why we took all the weight fractions up until 6, which is right before combat and after loiter. And since that, if we multiply all of that, it'll come with respect to the takeoff weight. So that one is the fraction we got as 0.8902. And after combat, we subtracted the expendable payload and the fuel weight, which we found from the formula above. And we got a weight fraction in terms of the takeoff weight, this last equation given here. So this was the combat segment of the mission. And this was the final takeoff weight estimation formula, which we took from Cork. We've accommodated for the reserve fuel here as well. And this was the empty weight fraction using I think it's called structure ratio. Using that, we've estimated this empty weight using the takeoff weight. And this is the formula which we used. And initially, we assumed a takeoff weight of 47,000 kg. After iterations, this is the weight we got, about 52,320 kgs. And
see, I'm a bit, where the second one, can you show me the emission profile?
Yes, sir.
See, you are getting only up to 6 prime. From 6 prime to 7 to 8 to 9, where is the fuel consumed?
Oh, sir, cruise and the cruise I've taken as similar for both, except I changed the altitude for the second one. And loiter, as I've already mentioned, was here, sir, for 20 minutes during descent.
That is okay.
For landing?
No. When you show finally, you are showing only for W6 prime. Where are they included? You are not showing anything there. Up to 6 prime, you have explained. W6 with W6 prime, etc.
No, sir, that is included in this this second part of the formula, where initially, since I've multiplied everything, that is what the fuel weight is, sir. I've taken all the weight fractions, which is here. These are all the weight fractions I've multiplied all of them and multiplied, since this formula is a little weird looking because of the 6 prime by 6, which has a takeoff weight dependency in the formula. I don't think
you might have made a small mistake here. I'm afraid. I'm not sure. Because don't worry about making it compact. Okay. But make the formula a little bit readable. In the sense, the first, you can make 3 statements also here, not an issue. In the iteration itself.
So this 0.825 accounts for the different weight fractions, sir, over here.
So that is before you drop the weight.
No, this is including everything, sir.
That's right. Don't jumble like that. I find it difficult to follow what you are doing.
All right. Okay.
Because now what I want to do is split it up into three or 4 statements in your report, or even your you split into 3 statements. Then you can show how you derived this. That is okay. That is what I want to see is first, how have we calculated the weight at W6 or W6 prime before drop. Then from that weight, you subtracted so much because you dropped so much weapon. Now with that reduced weight as the initial weight, you are going to the second iteration, second phase of your climb, cruise, and land. Okay. So now, if you combine all these 3, how are you getting this formula? Or is it different? Best thing is keep it separate. You keep all 3 separate, so you won't get into confusion. I'm not telling you are wrong, but to follow it is difficult.
Okay, sir. Definitely, I'll do that.
Yeah.
But we haven't taken the weights as such, sir. We've only multiplied the weight fractions before and after combat.
That will give you give you some wrong result. You try what I am telling, see whether there is some difference. If both give you the same thing, then you are right.
Okay.
That is, at 6 prime, you drop the weight. You have another weight. With that weight, you calculate how much fuel is consumed later. Now, finally, you get some weight, no?
Yes, sir. We have taken that into account here.
Right. Yes.
The fuel dropped, expendable payload, and the weight before W6. Now, since we don't have a value for W6, we took this W6 in terms of the takeoff weight, which is W6 by W
prime,
takeoff.
W6 prime by W6 is 0.185 minus this.
This 11,778 includes the expendable payload as well as fuel weight.
Okay, you're right. Okay, it's clear to me now.
Okay. Yeah, for W6, we took all the weight fractions until the 6th part of the segment.
Okay, you're right. Okay. Then from W6, again you are doing the W6 to W7,
yes,
W7,
sir.
W8.
Yes, sir.
Don't take the same fraction. The fraction will be different. Or is it you're taking the same thing?
Yes, sir. I think it said that the cruise value could be same. I changed the altitude and tried.
But loiter value will be different.
Yes, sir. That is
loiter
different.
Fraction.
Yes, sir. Okay. This time is 20 minutes and this is 25 minutes.
Where is W7 by W6? Not shown here.
Sir, that climb, we assumed that it wouldn't take too long. So the weight fraction, because from the altitude of combat to the altitude of cruise was pretty small, and since the rate of climb for interceptors is pretty huge, we neglected that weight fraction.
No, rate of climb is huge means you'll consume large fuel. You'll be using afterburner.
Yes, sir. I assume that as well, but
so what you should do is you have to include that here. W7 by W6. Maybe same thing use. It is 0.99 to 0.97 something use. Empirical.
Yes, sir. Okay.
Use that.
Okay. So the fuel weight fraction we got was 0.412 and this is the empty weight fraction.
Okay. Good. Any questions to Niveda? Already last time. Good. The presentation was crisp, neat, but within the time. I only prolonged it.
Not a
Anyway, how about others? Any questions? Okay, there are no questions. You can stop the recording, Sanjay.